Can you see the slide? Okay. So for today's presentation, what I'm going to present is PointNet, deep learning on point sets for 3D classification and segmentation. So there has been great advances in the field of 2D vision with convolutional neural network, but the world we live in is 3D dimensional, and in the field of AR, or advanced robotic systems, such as self-driving cars, need to process 3D information in real time beyond 2D image information. The current deep learning architecture for 3D geometric data requires highly regular data format, like image grids or 3D voxels. So the data comes in the format of point clouds or mesh need to be transformed to this regular data formats to be fed into the deep learning model. However, this data representation transformation renders data unnecessarily voluminous and quantization artifacts. For this reason, they focus on a different input representation for 3D geometry using simply point cloud. Then what is point cloud? Point clouds are simple and unified structure that consists of points with XYZ coordinate. Sometimes additional information like RGB value or normal could be incorporated. They are irregular regarding their density and unordered. Point clouds can avoid the combinatorial irregularities and complexity of mesh. When thinking about mesh, resulting representation of mesh is completely different depending on the vertices that make up the faces. Also, they are invariant to permutations and rigid motions. So rigid motion have rotation and translation. The last property of the point cloud will be explained in detail in a later slide. So to process point clouds, PointNet model was introduced. It is the most influential neural network architecture model for point clouds. It is a unified architecture that takes point clouds as input. It performs classification and segmentation. The output for the classification is class labels for the entire input. And the input for the segmentation is the per point segment labels for each point of input. So the key contribution of PointNet are as follows. First, they design an architecture that is suitable for consuming unordered point sets in 3D. Second, they show training strategies to perform 3D shape classification, shape part segmentation, and semantic parsing tasks. Third, they provide an empirical and theoretical analysis on the stability and efficiency of the mesh, of the method. Additionally, the idea can be extended to the other domains with the problem of processing unordered sets beyond the point clouds. So before we delve into the detail of the point, yeah.
In the previous slide,
yeah.
What did you see in semantic parsing tasks?
Semantic there is point clouds from scene, not an object. So they can segment chair or desk in the scene.
So that's a shape part segmentation, I guess. So if you say from the point cloud, you say that's chair, that's desk. So that's classification. The part segmentation would be, this part will be the leg part, this part will be the seat, this part will be the back. So that will be the segmentation. What is semantic parsing?
So I will show you. Oh, can you see? Can you see the slide?
Yes.
Yeah, so part segmentation is segmenting part of the object.
Yeah,
And
it's segmentation.
yeah. And semantic segmentation is when the scene is given, we segment the object in the scene, like wall or chair.
Okay,
Is
so
it
you
not
can divide
clear?
the scene into meaningful objects. I guess that's right.
Yeah, meaning
Objects. Yeah, so this is a desk, this is a chair, this is a wall, this is a floor. Okay.
yes. Okay. Oh, where was I? Yeah, here. So before we delve into the detail of the point cloud, we need to know the properties of point clouds. There are key properties of the key properties of point sets are as follows. First, they are unordered. Second, there exists an interaction among points. Third, they are invariant under transformation. Knowing the properties of point set is important because the key modules of the PointNet are inspired by these properties. So unordered means that the point cloud is a set of points without specific order. A network that consumes n 3D point sets need to be invariant to n permutation of the input set in data feeding order. So points in point clouds are not isolated and neighboring points from a meaningful subset. So the network has to learn the relationship between nearby points and the interaction among local structure. So the third property is invariance under transformation. As a geometric object, the learned representation of the input set should be invariant to certain transformation. Rotating and translating points altogether should not modify the global point cloud category, nor the segmentation of the points. So considering these properties, they have created three key modules of the network architecture. Let me briefly explain what it is. The network is using a max pooling layer as a symmetry function for unordered input, a local and global feature combination structure to combine the local and global information, and two joint alignment networks that align both input points and point features to the standardized space. In order to make the model invariant to the input permutation, they use a symmetric function. Symmetric function aggregate the information from its point. Here, a symmetric function takes n vectors as input and outputs a new vector that is invariant to the input order. You might be curious what symmetric function is. In mathematics, a symmetric function output the same value, no matter the order of its argument. Summation, for example, summation, multiplication operation, and max function is the example of the symmetric function. The idea proposed here is to approximate a general function defined on a point set by applying symmetric function on transformed elements in the set. The function can be approximated using multi-layer perceptron network and max pooling function. I made a diagram for further explanation. The network takes input point cloud with size of n/3. After applying transformation, the transformed input is fed into the MLP. Like this, Here, the function h is implemented as MLP. It takes transformed n by 3 input point cloud and then extends the channel from 3 to 64. I'm gonna explain about the transformation later. Similarly, the MLP consumes the transformed feature map to a feature map from 64 to 1024. This is what function h stands for. What about function g? This is a symmetric function. It enables the network to output the same vector regardless of the permutation of input point cloud. This is the point where the network can capture different properties of the set. The output from the symmetric function module form a vector, which is the global feature of the input set. We can easily train a multi-layer classifier on the global features for classification, but point segmentation requires a combination of local and global knowledges. To achieve this, computed global point cloud feature vector is concatenated with each of point feature. Then the network newly computes the per point features, which is used for predicting per point quantities like normal. So the last one is the joint alignment network. The semantic labeling of a point cloud need to be invariant to the geometric transformation, rigid transformation. They are not considering about scaling because they change the linearity and linearity of the points. So yeah, for this purpose, TNET is introduced in the architecture to predict affine metrics. The definition of affine transformation is a geometric transformation that preserves the line and parallelism. The overall network structure of the TNET is from spatial transformer network. STN, abbreviation of spatial transformer network, is a model for 2D image which computes the transformation that makes the input image orthogonal. Making the input image orthogonal is equal to aligning to a canonical space. Aligning to a canonical space is aligning all images to a normalized space while preserving linearity and parallelism between the points. Then STN applies computed transformation to the input image to make output image orthogonal. If we apply the main idea of STN to point cloud, it will be as follows. All input point clouds need to be aligned to canonical space, which center the point cloud around the origin so that all point clouds the network trains are standardized size. To achieve this, TNET need to learn an affine transformation matrix for all point clouds, which preserves the linearity and parallelism between the points. But the transformation matrix to be orthogonal matrix, which preserves the input information, they constrain the transformation matrix to be close to orthogonal by using this regularization term. The baseline for the experiment and result, they compare with the baseline, which include the multi-layer perceptron on unsorted and sorted points as n by 3 arrays. RNN, they also compare with RNN model that considers input point as a sequence. As shown in the figure, max pooling, what they use as a symmetric function, achieves the best performance by a large winning margin. They also compare the model with the previous works. PointNet achieves state-of-the-art performance among methods based on 3D input. Also, when compared with FoxNet, which is using 2D viewpoint averaging, PointNet shows much stronger robustness to missing points. More surprisingly, the learned shape global feature can be embedded into 2D space like this. And this is the result of the segmentation. This is end of my presentation. Do you have any questions? Thanks.
Can I ask you a question?
Yeah.
As the TNet is trained on the trained dataset, can it be applied to, can this pre-trained network apply to other domain? Can it can it normalize the different data from that dataset?
Yeah, I think it can be applied to other domains. What you mean is the TNet can be used for other application or?
Yes, other application with the point that has some different structure. I mean the size.
Yeah, I think they can be used for all data which have points, because when I implemented the TNet, the network was quite simple. They use very basic modules, so I think it can be applied to other scenario. It is not clear, right?
Thank you.
I'm sorry.
I have some questions, and I think it may be similar to Juan's question.
Yeah.
So I'm kind of confused about the input size, should I say? So if it's trained with the point cloud, let's say like number of points, let's say it's 80 points. And can it be also be used for predicting some classification or segmentation from the point clouds that has like 180 or 30 points or so on? Does it have, does this network restricted to the, what is it, resolution of the point cloud, or is it able to kind of like, yeah?
I think it can they can predict the point cloud with other resolution, because so points are sampled in the order of face size or the distance from the origin. So when new data set is given, the points would be sampled equal in the same manner. And yeah, I think they can predict the classification or K-score on the new data. I think it does not matter.
Yeah, I think the original assumption was that the cloud can be the distribution can be different. It can the ordering can be different. The density can be different depending on the part. The number can be different. Everything can be different. So it should work. And then I have a question why we are on this slide. When you explained this slide, you said linearity is broken. That's why we use TNet. I didn't quite understand that part. What's the importance of linearity regarding the linearity?
Linearity. So linearity. Fine trend. So we never change the relationship between points. It should keep the distance and the direction. So linearity. The scaling is not allowed in this PointNet to the PointNet because PointNet learns the relationship between points. So they only allow rigid transformation like rotation or translation. So they have to so they use the regularization term here to make the transformation metrics orthogonal. I think linear. I think I have wrong. I know the wrong definition of the linearity. Yeah, I got the definition now. Thank you.
I have a question about the TNet again. So
Okay.
in my understanding, the purpose of the TNet is to transform the point clouds into the canonical space so that the network can perform robustly no matter what the transformation of the point cloud is. I mean,
Yes.
the rotation and translation. But then I think the in the regularization term, the output of the TNet should be orthonormal, and I think
Yes.
there are no translation. I think so.
Yeah, no translation.
Yeah, I just wonder why,
Ah.
because the position matters, I think.
In the I don't know the exact reason, but in the code level, they also didn't apply translation. Only rotation. In the transform function.
Yeah,
But
I just
about
wonder.
the translation, couldn't it be like aligned to zero-centered by just subtracting the mean from the data? I think that is why they didn't consider about the translation. I think so. The main purpose is to make it like rotate the given data into somehow canonical space and to preserve the linearity. So if it's non-linearly deformed, the original shape grammar, should I say, would be kind of distorted, so it would not preserve the original shape. So they only just consider about the rigid transformation.
Yeah, it makes
Yes.
sense when there is only one object, but if I mean, there might be some cases where there are multiple objects in one scene, and there are no, I mean, if the points are scattered, then there is no way to distinguish this is chair, this is plane, or whatever. So I just wondered how they could deal with such cases.
I think they, for the scene semantic segmentation, they have to use new data set consists of scene, point cloud of the scene. So
Then is that data somehow aligned to some kind of certain origin coordinate, or?
yeah, they normalize point cloud into unisphere. Yeah.
I have a question.
Yeah.
So you showed us, in this side, they compared Foxnet and PointNet.
Mm-hmm.
So what is the advantage compared to the Foxnet? For the PointNet?
Yeah, Boxnet renders making the point cloud into voxel, and they capture the voxel from 12 directions, so they need 12 views, but PointNet only needs one view. No, just raw point cloud data. So for the computation, I think it is more efficient.
And you said you wanted to use the PointNet as a feature extractor.
Yeah.
Then what kind of information that you were trying to use? Like what exactly does it learn, the PointNet? Like other than the applications such as like segmentation. But I was wondering, does the PointNet like learns the relationship between the points, or like I'm not sure. So what kind of information does it like encode?
But is that interpretable? Since we do not know what kind of information does the VGGNet learns, we just assume that you're gonna do the job as we want to. And like, if you think of LXNet or VGGNet, it does what it meant to be, but we do not know their, latent space. So that's why we try to somehow entangle those information to be interpretable for the humans. So somehow to interpret those kind of knowledge, we need some analysis, but I don't know.
Okay.
It's a hard question, I guess.
Yeah.
Thank you. If there's no more question, I'm gonna end my presentation. Thank you for listening